Our next speaker is Danielle. He's going to tell us about MPC and dynamic incomplete networks.
So this is joint work with Ivan, Divya, Lance, and Sophia. So our goal is to establish communication between Alice and Bob. What I mean with that is a reliable communication or even a secure channel. Now, you might be wondering, we're in the MPC session, so I have to give you the disclaimer, the usual one. If you can do this, then you can do pairwise communication, take your favorite MPC protocol, maybe one from the session, and you have MPC. So that means we can now talk about this problem. Now, in many settings, it's very easy. So let's look at incomplete graphs. Okay, so we have a given graph, not all edges are present. Question is, how do we establish this graph, say, between Alice and Bob? And the answer is, okay, secure message transmission. We know that quite some while. So there's essentially results saying if this graph here is connected enough, then you can just do that. So therefore, let's make the problem a bit harder. We assume the graph is dynamic. That is, in each round of your communication protocol, you have a different graph. So now you can't plan ahead. And that is, before in these old protocols, right, everyone knew the graph, so you could say, let's send a certain part over this path, another one over the other one. It doesn't work anymore here because, it's changing. So let's talk about the exact setting we have here, because even though, if it's changing, right, if it's changing in a predictable manner, you can essentially, take the graph and add a time dimension, and then you can plan ahead. Therefore, that's boring. We look at the following. So we have n parties, one unbounded adversary. So, we could also be in the information theory session here. Then we also assume some of the nodes are bad. There could be two cases. You have active corruption, so they do whatever they want, or maybe they're just spies. They listen, they're passive, they want to learn the secret, but they follow our protocol instructions. Now, these channels we have here, we call them secure but unreliable. So that means the bad guys, they cannot see what is on the channel, but they get a notification about what happens. Like someone wants to send a message, but they don't learn the message. Unreliable here means the adversary gets notified, and then they can decide whether that channel actually works or not. Note that the sender does not learn about the outcome of this, so they don't get a success bit or so. And because we want to be fair in terms of communication complexity, if you want to use a channel, even if it doesn't work, we count that as communication. So communication here, right, we proceed in time steps, so it's a synchronous protocol, and we have a rushing adaptive adversary. So that is, in each round, the adversary sees where honest parties would like to send messages, and then the adversary can be, nah, I don't like that, and block some of them. So in our example here on the right, what you see is that only one of those messages actually arrives. Still, we would be billed for 2 messages in this case. So, of course, you now might say, okay, this is a really pessimistic setting, right? The adversary can essentially see communication and then block it. So clearly, if we allow any, things there, the adversary could just block communication always. It would be boring. Therefore, we need some guarantees on the graph. And so we say, okay, the adversary can delete certain edges in each round, but the overall graph we get per round must have certain nice properties, and the one we care about is connectivity. So, for instance, we could say, okay, the graph must be two connected, like the one there, the cycle. So that means in each round what happens is we have a potential edges, say the complete graph. Parties can then go and say, oh, I'd like to send a message to this guy. The adversary can then say, oh, the graph, it's the one to the left. Or maybe because they have a great day, they say, oh, all the edges are available. Communicate ahead. Okay, so that's the setting. Very pessimistic. And the question is, how do we achieve communication between Alice and Bob? So there is previous results on that, which essentially say, yeah, you can do that. But if you look at these results, right, the complexity, and I mean complexity both in round complexity and in communication, is not that efficient, even if talking to a TCC audience. And so the question is also here, the connectivity. You see there's some conditions. So if you want to do, for instance, a reliable communication with passive corruption, what we say is the graph needs to be connected in each round. Otherwise, it doesn't really work. And so the top three, they're necessary. And then this paper said, OK, the last one, this is, we conjecture it's necessary. So in our work here, what we do is we first of all show this is not true. You can do better. And we can also say you can be actually efficient, at least efficient in TCC standards, so polynomial complexity. So for the rest of the talk, some intuition about some of these results. Let's start with private communication. So I take the easy one, passive corruption. So the node corruption, they just listen to messages. They want to learn the message of Alice to Bob, but they will follow protocol instructions. And so the idea of the old protocols was essentially, first phase, we tried to establish some secret key between Alice and Bob, and then use that as a one-time pad. And to establish this secret key, what you do is you just try to send randomness over all possible paths. And that's crazy inefficient. So the question is, how can we do better? We use an old gadget here. So from the previous paper, there is the observation that if you just care about reliable communication in the passive setting, you flood. You just send a message along all edges. And so this gives you polynomial time communication. Note this gadget, of course, the adversary will learn the message, assuming there is at least one corruption. So we use that as a building block. So how can we do better than just getting exponential communication by doing this key flooding along all paths? Well, the idea is we use the metagraph. So in the first round, what parties do is they try to establish keys with all potential neighbors. So if I have an edge to someone else there, I'll try to send them a key, which in the information theoretic setting is just a lot of randomness, and I try to send it to them, and they try to do the same. And so what happens is the adversary will block some of the edges, but in some cases this actually succeeds. And at that point, what we have is the metagraph, which is essentially a graph of who has now a shared key with whom. This has nice properties, so it has high connectivity. So we assume here that the adversary needs to give us a graph which has a connectivity which is bigger than the number of corruptions. This graph now can be announced using flooding, so everyone essentially says, oh, I received some key material from these guys. And so now we have agreement on this graph, and we can use it for our communication attempt. So how do we communicate using this metagraph or on the metagraph? The idea is simple. If you want to send a message to someone where you have a direct key, well, you can use that key material plus flooding, and you have a private channel. It's just one-time pad communication. Then, so the interesting question is, I just want to point out, right, during flooding, the actual graph will change, but we don't care. Flooding is very resilient. So for the actual fun part is, okay, how do we do now Alice and Bob communication if they're not directly connected in this metagraph? And the idea is essentially secure message transmission. That is, in this metagraph, there will be, again, because it is highly connected, there will be T+1 independent path between Alice and Bob, and we can send the message along those edges, right? That is, we send it along those people, and we use the key material in the metagraph to protect communication. Because there's only T corruption, at least on one path, there are only honest people, so that means the adversary will not learn the message. Just want to point out that, of course, this whole communication can be parallelized in the sense that we do just one round of flooding and we're done. For the details, look at the paper. So then the other one, okay, so let's dial down on the requirement of our channel. It's just a reliable channel, but we up the game on terms of corruption. So now we have active corruption, so they're bad guys who can do whatever they want. They can send us wrong information, and the question is, how can we get efficiently a channel between Alice and Bob? So that's that. We're happy that the adversary learns the message. The important part is Bob should get the right message. The idea is, in the old paper was like, okay, flood the graph with metadata. Roughly, what you do is you try to send the message along every path, and each message comes with its like, oh, the message was going over these edges. Of course, the bad guys can pretend to do whatever, but in the end, there's a tricky way how Bob can decide, like, oh, okay, this message took this path and so on. If you received it over enough disjoint path, you can say, okay, this is fine. Problem, of course, is there is a lot of paths. So again, this is very exponential. not so nice. Therefore, the metadata is too big. What can we do? We can try to squeeze it down. So instead of having for each message that goes over a path, a separate metadata, we try to squeeze it down into what we could call a message passing graph. So if I receive the same message from two different sites, I'll combine the metadata. So in the end, what Bob receives is a message plus a graph over which this message traveled to him. And so it, of course, gets that for potentially many different messages. And now the question is, how do we find the right one? Now, it turns out there is a nice property in graph theory, a problem called labeled min-cut, which says, okay, what's the minimum number of parties which disconnects this graph? This intuitively, what this gives you, right? If this is small, that means you only need a few nodes to kind of cheat, to send a fake message. If this is high, that means most likely the message was going over one path which only contained honest parties, and we're good. So this is a way how to distinguish fake messages from real messages. The problem here, though, is, as Bob points out, is that this problem is NP hard. So of course you could say we're done, TCC, right? We have efficient communication, and well, Bob just gets a supercomputer. Question is, okay, can we do this slightly better? And the answer is yes. It turns out that we can cheat. There is a relaxed version of this problem called where we essentially allow fractional values. And it turns out if you have this relaxation, then there's a way how you can actually decide this efficiently. The idea is to use linear programming. And so this way, using this type of meta information, we can actually find out which is the right message and then get reliable communication like that. So overall, here are the results. So you have seen the squished metadata approach, and you have seen the metagraph approach. And for more information, have a look at the paper.